Hello everyone, welcome back. Let's dig right in. Until now you have been looking at general aspects which though impart practical knowledge can sometimes lead to issues when we are setting the question paper or such. So, we are going to move on to those aspects where I guess I can ask you some technically relevant questions, right. And the next aspect obviously is about risk assessment. In which context are we going to look at risk assessment, right? Before we understand something, we need to know why we are sparing time to understand it. So, when or in the succeeding classes, we are going to look at localized effects which are very much dear to us, as in water, wastewater or air pollution. So, when we talk about these aspects, we also need to know, okay, I am breathing in, let us say, polluted air every day because I am living in this city, in this locality and so on and so forth. But what does that entail, as in what is the risk to me? So, to be able to understand how to do that, we are going to look at this particular content. So, I am going to move on here. So, risk assessment. So, when we say risk, what is it that we are referring to, right? For example, what is the risk that you might what do we say face if you take my class compared to the risk that you would face if you take someone else's class, right. I mean, maybe you are going to have to put in more time, maybe more boring time or such, right. Or here it is the probability of an adverse outcome. So, in our context though, obviously we are talking about the probability of getting cancer, so carcinogenic risk, or probability of getting non-carcinogenic risk or non-carcinogenic risk, meaning there will be other adverse effects or toxic effects which are not carcinogenic. So, when we are talking about risk, we are talking about probability of an adverse outcome. The adverse outcome can be carcinogen, I mean cancer or non-cancer related effects. So, these are the aspects we are going to look at, right. Probability of adverse outcome. So, what do you understand when someone mentions that a particular activity is safe, in the sense that okay, someone says this water is good enough to drink. What does that mean? Does that mean that there are no contaminants of concern at all? Not necessarily. It means that the at that particular dose and at that particular frequency of drinking water, at that particular concentration of the contaminants in the water, these or this activity of drinking water every day, let us say for the next 20 years or so at 2 liters per day volume, does not pose unacceptably high levels of risk. So, that is what we understand when someone says that it is safe to drink this particular water, or when an activity is safe. That is something to keep in mind. So, as a natural corollary, that obviously means that there is no such thing as zero risk. It is just that the risk or the probability is so less. That is something to keep in mind. So, before we go further, I would like to give a local example much closer to home about why do I, or rather why should you care, right. That is obviously always the question. So, when you are on campus, obviously what is the water that you are drinking? You are drinking water from the groundwater, which is pumped up to the overhead tanks and then pumped to various localities within the campus. So, you say okay, my water is treated. Well, typically RO, yes, non-RO different aspects and such, but then you are going to bathe the water, you are going to bathe with the water, pardon me, you are going to wash your hands, so on and so forth. So, there are different ways that contaminated water can affect you. So, let us look at a particular example. So, we have different what do we say, labs on campus, departments on campus, which generate quite a lot of hazardous or chemical waste, sometimes biomedical waste, but that is tackled differently. So, you have a lot of compounds that are in use or used, let us say, right, and they need to be disposed of in a safe manner. Now, we have a hazardous waste what do we say, management system in place. All the hazardous waste is collected and then sent to a treatment, storage and disposal facility, which is one of the facilities we plan to visit or should have visited by now, right. That is a different aspect. So, if I do not dispose it in the scientific manner, what is it that people might have done or usually do? What can they do? They will put it in the sink. So, once this hazardous chemical gets into the sink, it is going to have to be connected to the sewer network, which will flow to the sewage treatment plant. But no network is airtight, and many of these compounds are pretty corrosive. So, they are going to leak through the particular what do we say sewer network, and contaminate first the soil and then the groundwater, which is again used by us. So, just a quick example here. So, here we have a marine core depot, right. Example is obviously from South Carolina. Why? That is where I could find data, but this is, as you are going to see, relevant to all of what do we say, or different aspects or different locations, certainly in India. So, here they have two facilities. One is the new dry cleaning facility and there is the former dry cleaning facility. Note that even everywhere in India we are going to have dry cleaning facilities. Dry in the sense that okay, I have a stain, so that is not hydrophilic, it is hydrophobic. The compounds that what do we say led to the stain, they are now adsorbed onto my shirt. How do I get them off? I am going to have to use a solvent, right, to be able to desorb the compound from my shirt. So, they are obviously going to use solvents. So, typically solvents have to be disposed of in a safe manner. All over India they are done differently. Here too, I guess they had some drums which were stored, and here they had a sewer network from the new dry cleaning facility, and the solvents were supposed to what do we say be transported to the sewage treatment plant. But both from the drums at the former facility here and even from the pipes here, right. Again, please note that it is very much, the scenarios are very much similar to what you would expect in India or on campus, right. Here you can assume that let us say this is one of our departments where different kinds of chemical wastes are used. Again, let me not go further into that. So, this is the scenario out here, and what happened, as you see over time they observed effects, and then you see contamination. So, this is 1000 parts per million, right, 1000 ppm boundary. So, a little further 110 concentration. So, this was from the drums. Again, whenever they had rainfall, the drums overflowed, and then again groundwater and such pollution. And here you see the pipes, these, if I am not wrong, these red colored pipes or these lines indicate the sewer network, and the sewer network obviously leaked, and all the solvent obviously leaked out and contaminated the groundwater. So, you see that again you have different buildings, you can think of that as your hostel. So, we have the compounds having leaked out. So, as you can see, though the source of contamination is out here, depending upon the groundwater flow, we are going to have contamination of a considerably wide area of considerably high concentration. That is something to keep in mind. And then obviously over time you are going to have contamination of a wider or greater area, and soon as you can see, you are going to have a considerable area that is contaminated at unacceptably high levels of concentration with just 2 point sources. Yes. So, this can happen everywhere. Okay, fine. So, what is the big deal? The big deal is that the solvents that they use typically, let us say perchloro, trichloro, and again vinyl chloride, these are all byproducts of PCE degradation. So, they were using, if I am not wrong, PCE, right, that is why you see more PCE here, and in the subsurface this PCE is being transformed into TCE, DCE, and then some of it into vinyl chloride, which is a remarkably carcinogenic compound. That is something to keep in mind. It is not just the primary compound is toxic or carcinogenic, but some of the byproducts of natural degradation are also very toxic or carcinogenic. That is something to keep in mind. Typically, we assume that okay, I threw a compound out and maybe it is toxic now, but soon nature is going to do its job and everything is going to be hunky dory, but that is not how it works out. As you see, if not quite often, there are quite a few cases when the byproducts of natural degradation are much more toxic than that of the initial product. Fine. So, as you can see, initially most of it is PCE, tetrachloro, and then I guess later dichloro or vinyl chloride and such, right. So, you have contamination over a wide area. So, this can happen in our campus. So, let us just look at what is going to happen if I drink water contaminated by vinyl chloride, right. So, we will look at the details later, but in general the cancer risk depends upon intake, right, how much I am taking per day and then body weight and so on and so forth. So, it depends on the current situation. Slope factor, this depends upon the type of compound, okay. More about this later, but this is called slope factor. So, legally 1 in a million, 1 by 10 power 6. So, 1 in a million chance is unacceptable level of risk for cancer. Okay. For non-carcinogenic compounds or such or effects, there is a different risk, but for this example, this is what we are looking at, that cancer risk anything more than 10 power minus 6 is unacceptably high. So, here this is a function of the concentration that we are taking and then slope factor just based on the compound. So, if I am taking vinyl chloride at 2 liters per day, assuming my body weight and assuming I am going to stay here for 35 more years, the exposure concentration at which I will have or experience unacceptably high levels of carcinogenic risk is 2 into 10 power minus 5 milligram per liter. Note that it is milligram and it is 10 power minus 5. So, you see that even if I just take 2 liters per day, that is, I believe that is the value that I use, 2 liters per day of drinking water, this groundwater, which has just 10 power minus 5 milligram per liter, right, over a 35 year period, I can get unacceptably high levels of or I am experiencing greater risk, carcinogenic risk. Okay, you say I do not care about you, I am here only for for a 4 or 5 year period, so you only care about me. So, let us see at what concentration will you face unacceptably high levels of risk, carcinogenic risk. So, 5 years, let us say you are going to stay here, or 4 years, and then the concentration at which you will face unacceptably high level of risk is still not too low, it is still 10 power minus 4 milligram per liter. So, you see, even if you do not care about me or us, you still need to care about you. So, that is why obviously you need to be concerned about what it is we are dumping everywhere. So, thus obviously I used based on the data from the US and then in India, but it is applicable everywhere. A dry cleaning facility is going to be everywhere, and if we do not consider or if we consider all the different labs that might have at one point in time dumped waste into the ground, or off campus, many of them do not have access to these treatment, storage and disposal facilities, you can understand the scenario, right. So, enough of that. So, this is the reason why you have to care, just some background, so that later when you are speaking to somebody or when you hear some data that okay, this is the concentration that you are being exposed to for so many days and such, you can then correlate it to whether it is correlated to unacceptably high or acceptable levels of risk. So, let us move on. And another aspect is it also drives legislation in the sense that a new pharmaceutical compound or drug has been found, not found, fabricated, let us say, and people spend billions of dollars on coming up with new drugs, but there are obviously going to be side effects. So, how do you go about looking at it? Let us say if there is a carcinogenic risk, people then look at again is the risk too high or the side effects causing cancer or any other adverse effect too high, again they are going to follow the similar procedure. I just wanted to mention that, right. Again essentially 0 meaning 10 power minus 6 or 1 in a million, right, virtually a safe dose. So, let us move on here. So, looking at 1 in a million chances, what are some of the activities and the types of risk, let us say. So, smoking 1.5 cigarettes per day, unacceptably high or 1 in 10 power 6 chance of you getting cancer and then heart disease. And I just wanted to share this because typically people think okay, it is cigarette smoking pretty bad, should not do that, fine. But even spending 1 hour in a coal mine will lead to unacceptably high levels of risk. Living 2 days in New York, but keep in mind that this data is from 1979 and now New York City is relatively better, but Delhi far worse. So, you can understand that living 2 days in New York City due to air pollution, the chance of death will increase or is unacceptably high, at least when we take the cutoff as 1 in a million, right. And then you have other aspects. One aspect I would just like to point out is drinking 12-ounce cans of soda in which you have artificial sweeteners like saccharin. I think they are banned or such, maybe you can look at it. So, even that particular aspect can lead to cancer. There are other aspects which you can look at for your own amusement. So, the receding 0 and such. So, if you say if you have TCE in your drinking water, let us say, would you drink it or not? That is what I guess I wanted to ask here. Would you take it? Or what do I need to look at? So, the issue is obviously it is all about the dose, right. So, just because a harmful or toxic compound or carcinogen is present in your water does not mean that it poses unacceptably high levels of risk. I need to look at how much I am taking, how much is there in the water, and then other factors, right. So, that is always the case, right. You need to obviously look at what do we say, different aspects. So, when people say in the past everything was pure and now everything is impure, it is also because we now have better analytical techniques to be able to detect compounds which we are not able to do in the past. That is one aspect, obviously, other than general levels of pollution now leading to pollution of the air or water. That is something I wanted to point out, because quite often people say okay, in the past everything was pure and now everything is what do we say, impure, because we are getting so much data. We are getting so much data because we now have better analytical techniques and thus lower method detection limits. That is one aspect. And then based on this, obviously if you are a manager, you can look at okay, how much money do I need to put in. Let us say the risk level is high, right, and these many people live in this area, and then you can, let us say if you are a manager and want to improve the quality of life, you will need to be able to come up with a number. So, then you are going to look at what is the cost per life saved. So, this was done again in the US for different activities. They looked at what is the cost per life saved, and they saw that with child restraints in the cars with which require this amount 1.3 million, let us say, it is you can obviously decrease the risk, let us say, or cost of what do we say, decrease the risk of death. For some, I guess it is way too high, but because it was present everywhere, they worked upon it, right. Again, a general example about how, let us say, you can look at the risk and then take a management decision about whether the amounts required are reasonable or not reasonable. Moving on. So, we are in this particular session or discussion session, we are going to look at risk assessment, right. So, here when we say risk assessment, again we are not going to ask you about any definitions or such, we just want to give you a working knowledge. So, it is the characterization. What are we characterizing? We are characterizing adverse health effects, right. Based on what now? When I, a human, am exposed to hazardous agent. So, it is a characterization of adverse health effects, let us say, right. So, obviously risk characterization, but what does this involve? It involves 3 steps. First, hazard identification, to know whether the compound is toxic, if so is it carcinogenic or non-carcinogenic or such, and then at what concentration am I being exposed to, or at what doses am I taking it in, and then for what dose, let us say, is what response can I expect in my human body, right. So, hazard identification, exposure assessment, dose response assessment, all these aspects, from this you can calculate the risk, right. And that risk is going to be communicated to the manager, and then the manager, or rather you, can decide okay, whether risk of living in this, risk is unacceptably high if I live in this particular locality. So, I want to move, or whether the risk is acceptable, and so I can make a scientifically valid decision to continue staying in this particular society or area. Or if you are the manager, maybe you can think of, let us say, spending money, if so how much, to be able to improve the situation, right. So, let us move on. So, hazard identification, agency for toxicology substances or registry and such, I think ATSDR or such, I will share the information. You can get, you more or less have information about almost all the compounds present in different sources. You can identify what kind of hazard, or if the compound is a hazard or not. Dose response we are going to discuss now, followed by exposure assessment, right. Let us move on. So, when we talk about dose response or toxicity assessment, first 2 aspects, as in am I talking about carcinogenic risk or non-carcinogenic risk. So, a compound might not cause cancer to me, but it can still lead to maybe some adverse effects, maybe some organs are going to be affected, or I am going to have adverse skin, what do we say, allergies or such, right. So, there are 2 different types of aspects we typically look at. So, here what do we have? How is the identified adverse effect influenced by the level of exposure or dose? Yes. So, now that we have we are able to understand that there are typically 2 kinds of risk, let us say air pollution, I am taking in a particular air pollutant because I am living in a particular locality or near an industry, and I am taking that in every day. Let us say that can lead to non-carcinogenic adverse effects. Yes, but then I need to be able to know for this level of dose that I am taking every day, what is the adverse effect and at what intensity. So, that is what we are going to look at. Again, we have data for all these aspects, but we will just look at how that comes about. So, typically sources of toxicity data, it can be human studies, but usually it is animal studies, right. Typically when you approve a drug, they are required to be done on animals, and depending on the level of approval, some human studies are also required, but we will just look at animal studies. So, why animal studies? Obviously, depending upon the type of animals that you choose, typically we have a species of rats and then rabbits. Rabbits typically, if you are going to look at neurological effects, rats for other effects in general, rats or mice. There are specific species of rats or mice that are acceptable. Why? Obviously, because the same effects that you would see in rats or mice are also well correlated with what you would see in humans, right. Human carcinogens are causing or cause cancer in these species of the animals. So, acute toxic doses are again similar, and biophysical patterns are also similar, right, and that is one aspect. So, typically where is it when I take a toxic compound, where do they end up? They end up in either the respiratory system, blood and the lymph nodes, liver, kidney, nervous system, skin, can affect the reproductive toxicity or embryo development, right. These are some aspects of, or some of the endpoints, and obviously if you look at the type of cancer, what is the types of cancer, you will see most of them are listed here. Why? They typically the compounds can, depending on the property, accumulate in these endpoints. So, a typical dose response curve. So, this is the dose, let us say 1 microgram per liter and 10 microgram per liter and so on and so forth. Adverse effects, let us say, is relatively milder one, let us say hair loss, 10% hair loss, 20% hair loss and so on and so forth, 100%. So, as you can see, we typically distinguish between cancer and all other health effects. Why? With respect to cancer, we are much more what do we say, I should not use the term pessimistic, cautious, right. So, we are going to be much more conservative in our approach when we are looking at cancer. For all other effects, we assume that is a different, there is a different dose response curve. Let us see what it is that we have. So, we have non-carcinogens, right, and again dose and then response or the severity here. We have different terms, it is easy to figure out. LOAEL is the lowest observed adverse effect level. I repeat, LOAEL, lowest observed adverse effect level, as in, let us say I am the pharmaceutical company, I am not going to spend billions and billions of rupees or dollars, right, in testing all possible ranges. I am going to test on the mice or rats at different concentrations over a certain period of time. So, I am then from that data you can observe what is the lowest concentration at which an adverse effect was observed, that is LOAEL. So, from that you can get this particular threshold, or sometimes you can get this threshold too, but rarely will you be able to measure this. And if you have sufficient set of data, you can also get this NOAEL, no observed adverse effect level, no observed adverse effect level, as in what is the maximum dose at which no adverse effect was observed. So, but typically companies try to go and measure this particular aspect. It is obvious why, I will not go into that aspect. For carcinogens, as I mentioned that it is going to be much more conservative. If you look at this set of data and this set of data, the primary difference that you will see is that here we assume, or we can see that the system or accepted scientific community, let us say, pardon me, scientific community says that we are going to have a threshold. Beneath this threshold, let us say this is 10, let us say. So, if I take it at 1 milligram per kg body weight per day, I am not going to have any adverse effects. But for cancer, you see that be it 10, be it 1 or whatever it is, we are always going to assume there is going to be a response. So, we are taking a conservative approach. So, there is no threshold here, that is something to keep in mind. So, if you remember, for our first example, I mentioned a slope factor. So, slope factor comes from this particular aspect, slope factor. And for non-carcinogens, you have what is called RFD or a reference dose. So, reference dose, that is what you would get from NOAEL or NOAEL for non-carcinogens, and for carcinogens you will get what is called a slope factor, right, that is what you have out here. So, but obviously I was just talking about or harping about the conservative estimate. Let us understand what that means. Okay, 10 lakh people or a million people jump from 100 meters, let us say 9 lakh die, and then linear extrapolation says that okay, 1 lakh people jump from 10 meters and then 90,000 die, okay fine. But 1 lakh people or 10 lakh jumping from 1 meter, it still assumes that 9,000 die. So, 1 meter not much, maybe as high as my waist let us say, and we are assuming 9,000 are going to die, and then 0.1 meter and so on and so forth. You see that we are being very conservative. This is what I wanted to convey with this example when I am referring to being conservative when we are talking about carcinogen related risk, right. Again, please note that why are we being conservative? First, we are testing the data on mice or getting the data from tests based on mice. There are other uncertainties, right. So, okay, let us move on. One aspect to note is that there is no threshold. Even at lowest doses, we assume that for carcinogens there is always going to be an adverse effect. And then based on the evidence, you already have compounds classified into different groups, A, which is confirmed as human carcinogens, and B1 and B22. So, other categories, but again issue to note is that depending on the drug and who is backing the drug and with what rigor you are testing, it can be classified differently, but when you look at different data and you seek A and B, you need to be remarkably careful, right, that is one aspect. So, I mentioned uncertainty factors and this reference dose or safe level or pardon me slope factor for the carcinogens, reference dose for the non-carcinogens, slope factor for the carcinogens. So, how do I get this reference dose, let us see. So, you measure either the LOAEL or the NOAEL and you are going to look at some uncertainty factors and then come up with this reference dose. So, that is something to keep in mind, right. So, what are these uncertainty factors, right. So, because let us say the effects on me might be different from the effects on you, you are going to have uncertainty factor of 10 for human variability, and because we are using the data from animals to extrapolate to the effects on humans, another set of uncertainty factors, and again 10 for less than chronic data, as in we typically do not have the time and money to test for the usual periods that one might be exposed to. So, if let us say usual scenario is I am going to be exposed to 10 years at a low concentration, typically the test might be done for 4 weeks or 6 weeks at a high concentration. So, because we are not using chronic data, again there is going to be another uncertainty factor, and obviously if you use LOAEL instead of NOAEL, another uncertainty factor, right. So, and then that is one aspect. If you remember, risk characterization was here, hazard identification was here, and dose response was here. So, I know what is the compound that can affect me, and I know some data now about the toxicity effects and at what dose what adverse effect, but I need to know what is the concentration I am going to be exposed to and how much I am taking every month or day per unit body weight, right. So, that is how it that is why is that relevant. Let us say a child is breathing in or taking the same dose as me, obviously he or she will be more affected, right. So, in that aspect you need to look at exposure assessment. Also, let us say there is an industry out here, okay, a bad example, industry out here, and you have pollutants being released. Let us say a person living right nearby, greater concentration might be more adversely affected or greater risk, obviously one living far away. So, I need to be able to calculate the exposure concentration depending to be able to calculate the risk, right. So, that is what I guess I just tried to draw. So, here we have a facility, then concentration in the air, I can either directly inhale it, right, and then I am going to have exposure and or intake, or if some of them have been deposited heavier particles into soil, then ingestion, or onto the skin, then dermal contact, again intake. So, there are different pathways. So, there are different pathways, that is something to keep in mind. Dermal contact, ingestion as in orally, inhalation as in through the nose, and so on and so forth, right. Again different aspects, but I will not go into detail here. So, exposure assessment, when we say exposure, what does it depend upon? So, one is intensity, as in how much, then how often am I taking it, and how long, right. How much am I taking, how often, and how long whenever I take it, right. It is more or less intensity, frequency, and distribution, pardon me, duration. So, this is a generic formula for any pathway. For different pathways, there will be different what do we say, intake formulas. So, it is the intake, what is it? Milligrams of the compound of concern taken per kg of body weight per day, and here we have the exposure concentration, rate of intake as in liter per day, exposure frequency, how many days per year am I being exposed to, exposure duration, how many years, body weight, and averaging time. So, for non-carcinogenic risk, the averaging time is typically going to be equal to the exposure duration. But for carcinogenic risk, averaging time will typically be the lifetime, and that we typically take to be 70 years. Again, you do not need to mug up anything, just need to be aware of the different variables. Obviously, as you see here, you are going to look at exposure concentration, body weight, and so on and so forth. All the different sets of data will be given. So, risk characterization, I mean once I get all these aspects, I can calculate the risk. For non-carcinogenic risk, you are going to have hazard quotient. Let us say I am living in an area where water is polluted and air is polluted. So, for different pathways, I am going to have different hazards here. So, for let us say air and then for water, right. How am I going to get this? I know that I can calculate the intake from this particular case, intake here, right. So, intake by reference dose will give me the hazard quotient for air and then for water. Then hazard index is the sum of all the hazard quotients. I am not sure if I messed up hazard, I mean used hazard index and quotient interchangeably, but you understand what I am saying. For different pathways and such, you are going to calculate the risk, right. And then this total, if the total is greater than 1, that means it is unacceptable. If it is less than 1, it means that it is acceptable level of risk, right. This is for non-carcinogenic risk. For carcinogenic risk, it is slightly different. So, it is carcinogenic risk, it is going to be calculated based on obviously intake into slope factor. This is what we did for vinyl chloride, which was a carcinogen, right. Intake into slope factor. And if this is less than 10 power minus 6, fine, it is safe. If it is greater than 10 power minus 6, it is not safe, right. Greater than 10 power minus 6, it is not safe or considered unacceptably high. This is for residential areas. For industrial areas, the threshold looked at is 10 power minus 4. So, the next time you see any data, considering where you are living in, and if you are being exposed to let us say concentration of I mean exposed to a compound at a certain concentration, you can easily do the math, just straightforward formula, and see whether the risk is acceptable or unacceptable. So, one aspect to note is that we think that okay, it is just a small dose, it is not a big deal, but it takes time for the adverse effects to come about. So, again there is a scientific basis, and I just wanted you to see that. And as I mentioned, to be a good student, not good student, pardon me, a responsible student, we request that you be a part of the hazardous waste management on campus. Please collect your waste. I am not going into the details about how, and store them. You can talk to your lab in charges if you are in the relevant departments, because every 3 months the treatment, storage and disposal facility will come, or rather they will send their personnel, they will take the hazardous waste and dispose them in a scientific manner, right. So, if you have any other concerns with respect to safety or such, you can talk to the safety office, right. They are in the main building, and as of now these are the people involved. And if you want to do more about or be a part of some of the nascent activities regarding the environment, including hazardous waste management, or let us say the Miyawaki forest and so on and so forth, you can get in touch with the ECHO group, which is a student group, and maybe take your passion through. So, with that I will end this relatively longer session, and thank you for your time.